Okay, so I think we will start.
Okay.
Today, I'm very happy that Rajesh Chaunsali will present his work. So he is a postdoctoral researcher in, I would say, more than 1 year or maybe 2. I don't remember.
About 2 years, yes.
2 years, yeah. Working on topological mechanics and nonlinearity. So I will let him speak now. Thank you very much for today's seminar.
Okay, thanks, Thomas. Hello, everyone. Thank you for attending the seminar. So today I'm going to talk about our recent efforts in the area of topological mechanics and its nonlinear extensions, which I have been doing recently. Okay. So it's a bit difficult to, so I'm going to talk with slides, but let's see how it goes. The outline of the talk is as follows. I'll go over a brief introduction of band topology. Then I'll take few examples in 1D, 2D, and 3D topological systems that I explored during my PhD earlier. Later part of this talk will be focused on several aspects of nonlinear topological mechanics that we have been exploring recently. So the topology we talk about here is not from the topological optimization that engineers are generally familiar of. It is more related to the mathematical topology that studies spatial properties that are preserved under continuous deformation of objects. So that means that, as you can see in the screen, that this cup and the donut has the same topology, and which can be characterized by the genus, which is simply the number of holes in these objects. Since the number of holes is 1, so these objects have the same topology. Using this, geometrical shapes of different objects can be characterized using different invariants. So as you can see here, different objects with different number of holes, so different topology. However, in condensed matter physics, which will be relevant here, we use topologies to characterize not the shape directly, but their dispersion bands. Okay, so let's consider these 3 crystals. Okay, can you see my cursor?
Yes.
Okay, let me. Okay, so let's consider these 3 crystals with varying atomic arrangements. You may say that these 3 are topologically, these 3 shapes are topologically same since they can be smoothly deformed into each other, right? But we actually look at the topology of their dispersion bands. So band gap in A, this is the band gap, cannot be smoothly deformed to the band gap in C without closing it at some point, which is shown in B. Okay, so that's why we say that configuration in A is topologically distinct from the configuration in C. Okay, and there's a way to calculate certain invariants from the spectral properties of these bands. Okay, and that makes these 2 configurations topologically distinct. The practical implication of this is that when we have 2 mediums with topologically distinct dispersions, we observe energy localization at the interface. Okay, so as you can see here that this is a lattice made of acoustic cavities, and the energy propagates only on the boundaries without leaking into the bulk. Okay, and neither it shows any scattering at the corners or around the defects. Okay, so one way to understand is this this figure is that we have the lattice which is of different topology than the system outside. And as we discussed earlier, the outside configuration supports a trivial band gap, whereas this lattice supports a non-trivial band gap. And in order to go from this configuration to this, at the interface, we must close the band gap, which means there should be energy propagation. Okay. So this underlying principle is called bulk boundary correspondence. Since we design the bulk, we are ultimately designing the unit cells in these systems. And we try to predict, or we try to characterize their topology. And then it gives a direct route or direct way to predict what happens on the boundaries of these systems. So after this short introduction, let me discuss a simple example of 1D topological mechanics that is inspired from the so-called SSH model. Okay, so let's consider a chain of spring mass system, which is a prototypical model to understand many physical phenomena. This is a periodic chain with two distinct interatomic springs with stiffness coefficient gamma 1 and gamma 2. And for generality, we also assign on-site stiffness to each mass. We can then analyze its dispersion by writing equations of motion for the two masses inside the unit cell. So these are simple Newton's equations. And since the system is periodic, we can assume block solutions and then come up with this eigenvalue problem where this matrix is the dynamical matrix as a function of wave number Q. We can then calculate the eigenvalues of this dynamical matrix to plot the dispersion diagram between frequency and wave number Q. So interesting thing about this matrix is that, first of all, it's a Hermitian matrix and its diagonal elements are the same. So this makes this spectrum symmetric about a fixed frequency. So as you can see here, where this omega square is the same as these diagonal elements. And note that the symmetry is seen when we plot omega square versus Q instead of omega versus Q. So in other words, the dynamical matrix is called chirally symmetric. And in a standard, this is one way to justify that it's chirally symmetric is by writing it in standard Pauli notation. So where these sigma matrices are Pauli matrices. And due to this symmetry of dynamical matrix, vector D, which has generally three components, X, Y, Z, DZ component is 0. So vector D only lies in XY plane. Okay. Whereas this is simply a shift about omega square, which is the frequency about which the spectrum is symmetric. So more intuitively, what's happening in the system is that let's consider three different cases of different relative strengths of gamma 1 and gamma 2, which are again two different stiffnesses of the springs. For when gamma 1 is less than gamma 2, we have a band gap between these two bands. And at the cutoff frequencies, two masses will oscillate in phase and out of phase. However, for gamma 1 greater than gamma 2, we have similar band gap. The band gap looks quite similar, but with a subtle difference where the masses have just the opposite behavior. This frequency corresponds to out of phase oscillation, and this frequency corresponds to in phase oscillations. So the band gap in this configuration is inverted compared to this band gap. Okay, and going from this configuration to this configuration, we must close the band gap at some point, which is basically gamma 1 equals gamma 2. And this is also known as Dirac point, where these two bands merge together. And this is equivalent to our earlier discussion, where I was talking about topology of dispersion bands. So we are essentially going from one copy to its inverted copy by uh, a critical point, which is a Dirac point. In order to get a topological invariant, we make use of the fact that the vector D, as I discussed earlier, lies in XY plane. Okay, so since in the dispersion diagram, the negative wave number at this point is equivalent to positive wave number at this point due to the periodicity of the Brillouin zone. What we have is that if we sweep all the wave numbers from this point to this point, the vector D forms a loop in XY plane. And for this configuration, which is gamma 1 less than gamma 2, this loop does not encircle the origin. Whereas the configuration which is gamma 1 greater than gamma 2, this loop encircles the origin. Okay, and this quantifies the topology. So we can calculate a winding number, which basically counts the number of origins or number of times the loop encircles the origin. So as you can see that in this case, we will have a winding number of 1. And that's why this configuration is non-trivial, whereas this configuration has winding number 0, and this is a trivial configuration. Okay, so you can for the later slides, the trivial configuration with a 0 topological invariant can be visualized with this orange with no hole, whereas the non-trivial with a non-zero winding number can be visualized with a bigger, with a one hole. Okay. So after we characterize the system at the unit cell level, we look at the more realistic system that has a boundary. So let us take this semi-infinite case to focus on the left boundary of the system. So this boundary we fixed. So when gamma, okay, so we calculate the spectrum of the system here, omega, versus gamma. Gamma controls the relative strength between these two springs, gamma 1 and gamma 2. So when gamma is 0, which means that both the springs are same and we don't have any band gap. But when gamma is non-zero, we have two different stiffnesses, and that's why we have band gaps on the left and right. Now you can see that these two regions have some difference, and the difference is that on the right we have another solution inside the band gap. Okay, so this is the physical manifestation of these two topologically distinct regions. So one topologically distinct system, one trivial system, which we discussed earlier, is gamma 1 less than gamma 2, that region, which is denoted by an orange. Whereas the right-hand side system, which has gamma 1 greater than gamma 2, is a non-trivial system. And physically, that system will have an edge state on the left boundary. Okay, so we can look at the solution of this particular mode and how it looks. And you can see that this mode is localized on the left boundary and exponentially decays in the bulk. By looking closely into the mode here, we can see that every even site has a zero displacement, and that's because of the chiral symmetry of the system. So to witness this topological transition, we designed this experimental setup. This is a vertically stacked chain of cylindrical particles. And due to the Hertz contact law, stiffness can be tuned by changing the contact angle. So these are 3D printed enclosures just to support the chain. And these enclosures can be independently rotated so that uh, we can tune the contact angles between these cylinders and maintain any stiffness distribution along the chain. We then excite the entire chain with a piezo actuator from bottom and measure the response using a laser at each location for each cylinder. Okay. So what we do here is we keep one angle fixed, which is 20 degree, for example. Basically, we are fixing one stiffness and changing other angle, which is changing other stiffness related to that. So here is the spectrum that shows a band closing at alpha equals 20, which is basically a configuration where all the stiffnesses are equal. So we don't have any band gap here. And as alpha deviates from 20 degree, we are able to open the band gaps on both the sides. However, these two regions are topologically distinct, as we discussed earlier, uh, depending on which stiffness is larger. And for the topologically non-trivial region, we see a mode which is inside the band gap. And this is the edge state in the system. And now we can also construct an interface. So far we have talked about an edge of the chain. Now we can join two different chains and create an interface in between. For example, here, this is a non-trivial and this is a trivial configuration, and we can join and make an interface. And here you can see it's a frequency versus space. The energy, there's a solution inside the band gap, and it's localized around the interface, as you can see from the amplitude. Okay, and this can be just reversed as well, but just by flipping the angles, and we can again see energy localization at the interface due to different topologies on across the interface. So the main message here is that it's a very interesting tool to confine energy in space by basically designing two topologically distinct mediums. So now I'll briefly go over some examples in 2D and 3D as well. So here we consider a thin elastic plate with local resonators arranged in periodic pattern. For the dispersion properties, we take a rhombus shape unit cell that has 6 resonators like this. The unit cell length is A. R is the radius of the resonators from the center. And for the hexagonal arrangement, as you can see here, by geometry, we have R equals A by 3. So now let us look at the dispersion in 2D of this lattice. So in the middle, we see for the hexagonal, we see the dispersion of the hexagonal arrangement with R equals A by 3. As we can see that we have something like the critical point we talked earlier. We don't have any band gap. And this is something called double Dirac cone, since we have 4 solutions which are degenerate here. Okay. So now when we change this radius R to a smaller value and larger value, what happens to this Dirac cone is we are opening it and we create a band gap. Similarly for the larger values as well. And what we see is that there is a distinct, there's a difference between these 2 band gaps or 2 dispersions. The difference lies in the modes. If we check the mode shapes of these points, as we discussed earlier, for example, the mode shapes of this point look something like p orbitals, whereas these look like a d type. For the larger radius, what we have is just the opposite. So essentially we are having a band inversion in the system. Okay, this phenomena mimics the so-called quantum spin Hall effect. So what we can do from this phenomena is basically we can construct a lattice by adjoining lattices of let's say different radius. So one is with enlarged radius, bigger r, and this is with smaller r. So these 2 are topologically distinct, as we have seen. Now what we do is we excite the system at the interface. So there's an interface of this shape here. The excitation is out of plane. So we predominantly excite the flexural modes since the plate is thin. So what we are observing is that we are able to confine energy along this interface, and also that the wave doesn't backscatter at these corners. So this is very interesting phenomena. And there's another interesting thing about this is that when we look at the wave propagating towards the right, it has this typical pseudo spin, so which is clockwise, as you can see here, whereas the wave propagating towards the left has a clockwise pseudo spin. Okay, so now we can actually utilize this spin characteristics and give a spin dependent excitation to the system. So here initially we can have a multiple point excitation with a phase difference, so that we selectively excite only clockwise spin. And due to this topological system, what we are able to see is that we have a one-way robust wave guiding in the system, which does not backscatter at the corners. Okay, so for the experimental design, we took a thin aluminum plate with only 1300 bolts. So this took a few days to basically assemble all these bolts. And then this was the final prototype. And this is how we measure the plate vibration. So plate is stacked vertically with these 2 distinct regions with different topologies. And here is the interface. We excite the plate using a piezo actuator, and a laser measures the out of plane velocity of the plate point by point. And then we scan the entire plate and reconstruct the wave field. Okay, so here you are going to see the experimental results showing the out of plane velocity. At the center, we are going to excite the system, and we will see that the energy will be will be guided along this path. And also we will notice the spins. So the counterclockwise spin propagating in this direction and clockwise in this direction. Okay. Yes, so there's another effect called quantum valley Hall effect, which we explored. So here the lattices are made of bistable elements with two stable states. So one state is denoted by yellow color, other one is denoted by purple. So in this lattice, we can maintain these states alternatively. So if this is Y, this is P, Y, P, Y, P. So we can construct a lattice like this and just flip Y and P states in the other configuration and join them. So we have an interface with two different topological systems. Okay. Now, here, what I'm going to show you is a comparison between trivial waveguide and topological waveguide. So for this configuration, we are going to see how wave propagates in this simulation. Whereas the trivial waveguide here, we just construct by, not by taking topology into account, but by simply removing some defects or by creating some defects around the interface and then sending a Gaussian pulse and see whether we are able to channelize the wave. So let us see a trivial waveguide and a topological waveguide. A Gaussian pulse propagates, it's able to go here, but as soon as it tries to bend, there's a significant backscattering. Whereas for topological waveguide, we don't see a significant backscattering, and we are able to very efficiently propel the wave in the structure. So there's another topological phenomena which we explored using our bolted plate system, which is related to higher order topology. So here, essentially, the systems are same. So we have a lattice with a smaller radius and lattice with a larger radius. When we create such a configuration, what we see is that there's an energy localization at the corners, okay, instead of a wave propagation on the interface. So this is called higher order topology. That's because we have a system which has a spatial dimension of 2, but the localization which we are talking about has a dimension of 0. So we have a 2-order reduction in the localization phenomena, because earlier what I showed you a 2D configuration which has a wave propagating in the interface, which is basically a 1D phenomena. But now this is a corner mode. This is just a localized standing wave. Okay, so this also was quite interesting. And then we can also construct, we can rearrange these boards in a non-periodic pattern to mimic something called Dirac vortex. So essentially what happens is that we have a band gap in all the directions in the system except the center. And because of that, we are able to localize energy at the center of the structure. So finally, just a quick glimpse on topology in 3D. So this structure is made of beams. So each unit cell here is something like this, where we have two hexagonal layers which are coupled by these cross beams. Okay, and this gives the system a chirality. Okay, and the mechanism here is based on wild physics, which I won't go in detail. Essentially, what happens practically is that in this structure, if we excite somewhere on the boundary, what we see that energy propagates around the surface and doesn't backscatter at the corner, and also there is a defect created and it goes around the defect and it doesn't leak inside the bulk. So this is very interesting way to channelize wave or channelize energy into a 3D structure. Okay, so I'll take probably 1 minute break, and then I'll go over nonlinear aspects of topology. If you have any questions by then, maybe please feel free to ask. Okay. So you would have realized by now that topological mechanics depends on linear dynamics. We talk of dynamical matrix, we talk about eigenvalues, eigenvectors, dispersion curves, and so on. So these are the concepts of linear wave dynamics. Now let me discuss our recent efforts to understand the role of nonlinearity in such systems. So first of all, why we are interested in nonlinear topology. So first is that a nonlinear system can have amplitude-dependent frequency tuning. And also it can tailor stability of these solutions, which we have discussed earlier. We are also interested in looking at new solutions, which are, for example, tsunami-like soliton solutions, which are very unique to nonlinear systems. And these emerge due to the balance between nonlinearity and dispersion in the system. And the final goal or final is a big question in the area, is that how to define invariants when a system is non-linear, because we calculate these invariants from dynamical matrix, again, assuming a linear dynamics, okay? So these are different aspects of nonlinear topological mechanics, which we have recently explored. So I'll go over those one by one. These are, these are some exciting directions we have recently looked at. So first is the stability of topological states in nonlinear systems. So here you can see that we have a similar system of springs and masses with two different stiffnesses. Now what we are doing here is that we are introducing nonlinearity in these on-site springs, and the nonlinearity type is cubic. Okay. Now we already know that the linearized dynamics, where capital gamma is 0, we have seen this picture earlier, that we have these two topologically distinct regions depending on what the gamma value is. Okay. And this is topologically trivial, this is topologically non-trivial, and that's why we have an edge state here. And the edge state looks like this, where the even sides have 0 displacement. Now, if we have nonlinearity in the system, so when we have non-zero gamma, and in particular we have gamma which is negative. So negative means we have a softening in the system. So what happens to the edge state? So we are focusing on this solution, and we are increasing the energy in the system. And since nonlinear systems are energy dependent, amplitude dependent, we have change in frequency as we change the total energy of the system. And now this solution decreases in frequency and then enters into the acoustic band, which is down below here. Okay. So this is this is what we expect from a softening system, right? So what's interesting is that when we look at the mode shapes, or we look at the nonlinear periodic solutions at these points, we have non-zero displacement, which was not present in the linear dynamics. And this is the sign of breakage of chiral symmetry due to nonlinearity. Okay, so now in order to understand the stability, so since the nonlinear system is amplitude dependent, it's natural that we have to analyze whether the small perturbation to the nonlinear periodic solutions can grow exponentially over time. And this is nothing but instability in the system. So this is how we analyze the stability. We take the same chain, and we can write all the displacement and velocity and construct one first order differential equation. And then we can write a variational equation around a periodic orbit. So if the nonlinear solution we are talking about is Q0, we give an initial perturbation to it, which is dq, and see how dq changes over time. Okay, so essentially the dynamics of dq is governed by the so-called monodromy matrix. Okay, and the eigenvalues of monodromy matrix dictate whether the solutions are stable or not. Okay, so here when the eigenvalues are greater than 1, or their magnitude is greater than 1, we have instability in the system. So now let us look at the same softening system we talked earlier. So the system frequency decreases, and all these solutions, we can see that here we plot the maximum eigenvalue, and all these eigenvalues deviate from 1 unity, which means that all these solutions, all these edge states are unstable. This can be confirmed by long-time dynamics as well. So here what we do is we take one such nonlinear edge state, and we give that as an initial excitation, initial condition to the chain, and let it go over time. Okay, so this is the transient simulation. As we can see here, this is space and time. Initially localized state loses its energy into the bulk, and it's no more localized. Okay, and this is the short time Fourier transform of this state. The initial excitation was given at this frequency, and over a long time what we see is that this goes back to the linear edge state frequency, which is here, by shedding its energy to the bulk. So now we take the similar system and take a stiffening nonlinearity, where we just change the sign of capital gamma. Okay, so what do we expect? We expect that solutions here frequency will increase. So this solution frequency will increase and go to the optical band, and this is what we see here. But what's interesting is that the stability trends are drastically different. So we have a region of actually stability where high amplitude solutions are linearly stable. Okay, and this let me stress that this is a large band gap. So we have a strong nonlinearity in this region, but we are still able to have these linearly stable edge states in the system. And this can be confirmed again with long time dynamics. This is the initial condition to our chain. And we can see that for a long time, this state remains localized and its frequency also doesn't change over time. So ultimately, the message here is that the stability of these topological edge states depend on the nature of nonlinearity. So it's very important to specify what kind of nonlinearity we have in the system. Okay. So another aspect we explored was a self-induced topological transition. So here, you know these figures by now. You know oranges and bagel. What we are essentially talking about is a trivial and non-trivial lattices. But in a linear regime, these systems were different with different stiffnesses. Now, the question we asked was, can we use nonlinear effects? Can we use amplitude dependency in the system to go from this state to this state in one single system without changing any other parameter, just changing the amplitude or just pumping the energy in the system? And can we change the topology? Okay. So as we can see, what essentially we want to design a system where when we excite with a small amplitude, we don't have any edge state. Whereas when we have a large amplitude, can we have an edge state here due to the topological transition? So for this, we have again a spring mass lattice where the nonlinearity is of FPU T lattice type. So these are interatomic nonlinearity, as you can see here. But the key point here is that we use two different types of nonlinearity. So in one spring, this is a stiffening type, and the other spring is softening type. So one is a plus, one is minus. So stiffening is a hardening spring like that, and softening spring like that. And then we focus on small band gap and weak nonlinearity. So it means that small gamma and capital gamma both are small. And such systems in mechanical domain could be realizable, and that's what we are trying to explore right now. There have been systems where by changing the geometry of the system, we can tailor the nonlinear response. So it's quite possible to have softening and hardening in mechanical systems. So one may ask, why two types of nonlinearity in the system? It's because as we have seen earlier, these three cases leads to a dynamical matrix where the diagonal element is the same, and this is the center frequency here. So we want to maintain the chiral symmetry in the nonlinear system. So what essentially it means that we want to maintain what the effective diagonal looks like. So effective increase in gamma 1 by stiffening nonlinearity should be balanced by effective decrease in gamma 2, which is softening nonlinearity, so that the effective term, diagonal term, remains the same, and we have we have the chiral symmetry in the system. Okay, so I won't go into detail, much detail, but let me just rush through because I think time is almost over. So we have this chain, and then we can simply write the equations of motion. And this is the linearized system. What happens when gamma is 0? So we know that there's a band gap here. And we also know how these solutions look like. These are in phase, these are out of phase. Now we can use these substitution. Basically, we can make use that wave number here is pi, which means that we can basically reduce these alternating values to these constant values here. Okay, and this basically eases us to use continuum approximation on U and V. Okay, So when we use continuum approximation for this system, we get these ordinary differential equations. And then basically what we can show is that by changing the amplitude in the system, these cutoff frequencies will evolve like this. So what essentially is happening is that we are able to close the band gap and open it again just by changing the amplitude of the system. So we have this so-called band inversion, but just by the nonlinear effect in the system. So in order to analyze the whole family of solution, the best way is to look at the phase portrait of these differential equation. So this is for the omega 0, which means the mid-gap frequency. We are talking about solutions around this point. And this is a beautiful phase portrait, U versus V. I'm not sure whether how many people will be familiar with this, but just for the comparison in the linear dynamics, we have a phase portrait which looks like this. This is essentially talking about a region which is very close to the origin where U and V are very small. So we are very in a linear limit. But as we go to nonlinear region, we have these new solutions coming in the system. And what we found is that in this, the domain which is inside this trajectory shown by green is topologically trivial, and outside is topologically non-trivial. And this trajectory is actually a soliton solution, which is the heteroclinic orbit connecting two fixed points. So let me show you how the solutions look like in this nonlinear system. So for example, in this, let us look at a solution inside this circle. So the solution, we have a vibration like this. The solution on this trajectory, which is a soliton trajectory, we have this king soliton. And when we go outside, we have this solution, which is very interesting. We have a localization on the boundary, but it doesn't decay to 0, and it saturates to a constant value as we go in the bulk. So I'll recommend if you are interested why these are topologically distinct regions, but to mention it very briefly, what we have is that in this domain, which is the one inside, gamma 1 is always less than gamma 2, which is the effective stiffnesses of softening and stiffening nonlinear springs. So as we can see that along the chain, this is always less than gamma 2, whereas for the configuration outside, we have gamma 1 greater than gamma 2. And for the soliton, these two exactly match. Okay, so this is something like orange, this is something like bagel, but the difference here is that the topological nature is seen more locally, as we are seeing this since because the system is nonlinear, the effective stiffness would change along the space. But interestingly, wherever you go in the space, we have this relation which holds true. So that's why this is topologically non-trivial and this is topologically trivial. So when we have this system and we want to do, let's say, experiments, we have a finite edge, and let's say we excite this system with a Gaussian pulse with different amplitudes. So what happens? So when amplitude is small, we have a pulse propagating, which is dispersive. As we can see that we have a band gap, and the wave which has a frequency inside the band gap that doesn't propagate. But there's a critical amplitude around which we have more localized propagation, and we are effectively able to close the band gap. And as we go higher in the amplitude, what we have is that we have an edge mode or edge localization in the system. So we can clearly see that we have an edge state due to nonlinearity induced topological transition. Okay. So there's okay, let me go over another aspect which we looked recently, which is something called Dirac Soliton. So we take FPUT type lattice, where again we have all intersites springs which are nonlinear with the same nonlinearity. Again, we look for weak small band gap and weak nonlinearity. So essentially, this band gap is small, and we are looking for the solutions inside this band gap. And we can write effective, we can use continuum approximation and write effective PDEs in this. And these are standard nonlinear Dirac equation in the system, which is very interesting because these systems or these equations have Dirac solitons. As you can see here, a chain will have a localized nonlinear solution which vibrates like this. Okay, and this is a Dirac soliton. And now, since this is a stationary Dirac soliton, we can also have a moving Dirac soliton in the system. And what essentially we are trying to think is that we can design structures where we have these Dirac solitons moving along the chain. And when they reach the edge of the system, they excite a state on the edge. Okay, so which is something like coupling a bulk mode to an edge mode, which is not possible in a linear system. Okay, so this is simply this is purely because of nonlinearity, which we are able to basically utilize to couple the bulk Dirac soliton to an edge state and remotely excite the edge state. So this is very interesting aspect we analyzed recently. And then the final aspect which we investigated was that, okay, so we have been talking about these topologically trivial and non-trivial systems. And what I have shown you till now is that edge state exists for a non-trivial region. Now, is it possible that a trivial region can also have an edge state, but can we use nonlinearity for that? Okay, so this is the question we wanted to address. And the answer is yes. So as you can see here, we have a nonlinear system with an edge. This is in the linear limit. This doesn't have any edge state here. But when we kick in nonlinearity, this is again optical and acoustic band, and we are basically doing the continuation analysis for the optical mode. And we find, without going into detail, we find a new family of states, which is basically localized on the edges of the system. Okay, so one family is stable, which is the dark here, and the unstable point is here. Okay, so the idea here is that we have a self-induced edge state in a topologically trivial lattice. Okay, so finally, let me conclude with some challenges and future directions regarding the nonlinear topological mechanics. So for sure, there has to be a lot more exploration of interplay between topology and the nonlinearity. What I have shown you is just a glimpse of a different phenomena, which might be interesting. But fundamentally, there's a lot more to do. Then you have seen that different functional forms or different nonlinearity can change behavior in the system. So this is also interesting to explore all different sorts of nonlinearity and find novel phenomena. Then most of the studies are done for small band gap, for continuum approximation, where the wavelength is large compared to the lattice size. But when we have discrete effects in the lattice with high nonlinearity, can we say something about topology. So these aspects are very, very open, and there's a lot to be done in these aspects. And then, of course, we can extend these ideas to higher dimensions and then higher order topological systems, as I talked in linear systems. And then, of course, experimental demonstrations are very, very rare in nonlinear topological mechanics. So that's a challenge, and it's an ongoing effort which we have been involved in. So finally, I would like to acknowledge Yorgo, who I have been working with here, and then my PhD advisor, Jingku Yang from the University of Washington, and all the collaborators. They have contributed in this work. Yes, so I thank you for listening, and I'm open to questions.
Thank you a lot. Is there any question? No, there is no in the chat. I just
Okay.
fill it with the program of the next seminar at the beginning of your talk. You said that for the nonlinear experiments you were working on that. Maybe you can say a few words.
Yes. So that's a good point. Let's see. Yeah, especially for something like this system where, as I said, we need stiffening and softening type of nonlinearity, right? So we have been looking at some configurations where, for example, geometric or topological optimization can be used to optimize the geometry to have this hardening or softening behavior, okay, which mimics this kind of nonlinearity. Okay, so primarily, yeah, it has been more into topological optimization and looking for the optimized geometry.
Okay.
But that's ongoing. We haven't been successful yet in that. But of course, there are other configuration, other phenomena which doesn't require this kind of nonlinearity. So as I showed earlier, and those definitely we will look as we proceed in theoretical aspects first.
Yeah, with the Soliton, Dirac Soliton things, you plan some experiments with that, or?
Yeah, so for now, we were trying to explore the physics, because that's not, again, it's a new field, and not many things are known. So we would like to understand the phenomena first, and then, of course, yes, experiments will be very, very interesting. That's the next step.
And talking about experiments, can you go back on the one for the linear case, please? The plate. Yeah, I just missed like how you did the measurements or all these things.
Okay.
Yeah.
For example, this one.
Yeah, please.
Okay, so basically we have a plate, and then these are bolts, right? And we construct this interface by these two. These are two different topologies, right? Where the radiuses are different. And now we excite the plate using a piezo actuator. We glue a piezo actuator on the plate.
On the other side?
Then,
or no?
No, just, yeah, to the other side. Yes, yes. And then we measure the out of plane or the flexural vibration of the plate using a laser Doppler vibrometer, point by point on the plate. So we move this two-axis linear stage.
Okay. And so that's how you obtain the movie with the localization of the...
Exactly, exactly.
Okay. There is, okay, thank you. There is a question in the chat from Jean-Michel about slide 4.
Slide 4. Okay.
But it is asking about your choice of color in the bottom row, I guess. But yeah.
Choice of colors here.
Yeah, for the inverted band gap, why there is a blue piece that comes to the red?
Okay, that's a good question. So yeah, the physics is a bit different, but essentially, okay, in order to understand, we can say that there's a band inversion in a which is a bit local, okay, so near the Dirac point. Instead of having inversion of the entire bands, if we see locally around the Dirac point, means locally around this area, we have this inversion. But more mathematically, this phenomena is associated with very curvature, so it leads to curvature, and this basically color difference what you observe is it has the mathematical meaning basically, okay. But when for now I think it's relevant to just look at the local region here and then observe the band inversion. But this is actually important. Yes, this is not, it has a physical meaning. This is not random color choice here.
Yeah, I guess. Theo has a question on the experiment on the interface to 1D system. Maybe Theo can speak.
Okay.
Yeah. Hi. First, thank you very much for the presentation. So I just wanted to understand a bit more about these experiments. So on the left-hand side, you have the non-trivial topological state on the left and the trivial one on the right, whereas it's the opposite on the right-hand side. But on the experiments on the bottom, it seems that the discrepancies between the eigenanalysis and the experiment is only located on the left-hand side on the cylinder index. Can you explain why?
Let me, so you mean a discrepancy
Yes.
here in this region?
Yeah, yeah.
Well, there's a discrepancy here as well. Right, but
yeah. But this is the main problem I don't understand, because the system is not the same. It's reverted in.
Yes, I mean, so good question. So thing is that in the experimental setup, when we revert it, our initial, because we are exciting this using a piezo actuator, you see here. So when we revert a system, our initial here the configuration is changing, right? Even this part, and also first of all, let me comment on the discrepancy between these, because experimentally we have an evanescent wave, okay, which is decaying, which we are not capturing using the eigenanalysis, because that's giving us just the real solutions in the system. So that doesn't capture the evanescent wave. So that's why there's a difference between eigenanalysis and experiments, at least in the initial region. And that's actually good, because that's how we are able to excite the mode which is at the interface, because our actuator is not located here, right? Our actuator is located on one end of the system. But since the chain is short, we are able to couple this energy and excite the system. Does it make sense?
Yeah. Thank you. Yeah. And also congratulations, because this presentation was very clear. I think not all of us are familiar with topological states and so on, and I think it was very clear.
Thank you very much. Thank you.
So if nobody has any more questions, we can thank again a lot Rajesh for this really great presentation. I will stop the